today we are discussing first the definition of a wave front. Alright students, so what is a wave front? So reflection of water waves. So students, you understand what is reflection? Reflection is kind of bouncing back. Now we will talk about what diffraction is. So diffraction is basically the spreading of wave. Here we are talking about that change, that the medium has changed, the water quality has changed. In a way, deeper the water, what will happen is that the surface will be way away from the bottom. Hello students, welcome to your own physics class. Students, today we are continuing with our unit on waves. So much we have already talked about. What are the basic parameters associated with a wave? What do you mean by a wave? And last class precisely we were discussing about water waves, the waves that travel on the surface of water. So I hope you are able to correlate things so far, and if you haven't watched those videos, then it is my strong recommendation that you watch those videos first and then you can come back to this video. So when we say wave, students, I hope you remember there are two main waves that you encounter around you. One is sound and the other is light. So now we are going to start with the detailed discussion on sound waves and following it up with another video where we will be discussing about light waves. Right students? So I hope you are all excited and willing to learn how to encounter this. You learn them, you know them, and you will be able to do all the questions. There is no baggage of learning too many formulas in this unit. It is a very simple unit in that sense that you just have to understand things and you're good to go. Right students? So sound, of course, there's no doubt about it. You do understand what do you mean by sound wave. So for example, if you are talking, then what is happening? You are basically creating a pattern that is propagating and reaching the other person's eardrum, and that is how you perceive sound. So vocal cord, it starts from your vocal cord and it terminates at the eardrums of the other person, right? That is how sound, you are using sound as a way of communication, right students? So sound, put down the heading sound. Alright, so now if you are all geared up, let's start. Sound waves, there are a lot of things I wish to talk about. First is properties of sound waves. So of course the first property that you should know is that they are longitudinal. They are longitudinal. Second, they are mechanical. Okay. So when I say sound, it is basically propagation that happens due to a repeating effect that particles of the medium transfer further and further, which is only possible in solids, liquids or gases. So you need medium for sound to propagate. If in vacuum, imagine in space where there is no medium, there is no air, sound cannot travel. For sound to travel, you need medium. They are called mechanical wave. While the other version of wave, light, that is where you don't need medium for it to propagate, right? So sound needs medium to propagate. They are mechanical waves. Properties of sound, they are longitudinal. Since they are longitudinal, I hope you remember in the last class we have discussed, it is accompanied with formation of compression and rarefactions. Compression is where the particles are closer together. Rarefaction is when they are further apart, as you may see in the diagram, right? Compression, rarefaction, right? So that is what is formed. So when I am talking, there is a continuous formation of compression, rarefactions of the particles in the air, right? Okay. Next, behavior of sound waves. How do they reflect? How do they refract? Right? How do they diffract? So I hope you are now knowing that how our study is going in this direction. Every time we take up a task of understanding a wave, and then the three phenomena that we discuss related with that is reflection, refraction and diffraction, right? Measuring speed of sound, loudness and pitch. Okay, loudness and pitch. So I hope you understand the basic parameters like frequency. So a high pitch is basically a high frequency sound, right? High frequency means high pitch. So frequency is how frequently the waves are being formed, number of waves formed per second. So pitch is just a relative term. So for example, if I am talking and one more of my friend is talking, we both might have different frequencies, right? So if let's say I have a lower frequency, the other person has higher frequency, then you would refer it as high pitch voice for the other person. So frequency is basically the decider of pitch. More the frequency, more the pitch. It is just in context of the observer. It is a relative term. So if you are comparing two sounds, the observer will refer one sound as high pitch, the other is comparatively lower pitch. That simply implies the first person has higher frequency and the second person is lower frequency. So frequency is normally stated for the source, but when the observer or the listener will refer to it, they normally refer to it as pitch. Okay. Measuring speed of sound, we will discuss how we can make use of different experiments to measure the speed of sound in various medium. Then sound is obviously produced by vibrating objects, there's no doubt about it. You start hitting the pen on your table and this will create a sound, right? So this sound is basically created by oscillating particles, as we may know, right? Sound waves are mechanical waves, we do understand that, and sound waves are longitudinal waves. So I have written everything for you. You should also write all this. A mechanical wave needs medium to propagate. If we pump out air from a vacuum jar, the sound of the ringing bell becomes quieter, right, students? So if we keep pulling out air and we start creating a vacuum, then eventually you will realize that the sound has vanished, right? No matter how high the oscillation is, you won't be able to, because then it does not propagate. There are no medium particles to replicate the pattern, right? So astronauts need communication devices because they cannot hear each other in space, because sound does not travel in space. Keep this in mind, sound does not travel in space. I have referred to this. One last thing is the loudness of sound, students. So imagine, what do you do with an amplifier? What do you do with a microphone, let's say? So a loudspeaker, let's say. So a loudspeaker creates the same sound with greater amplitude. So for example, if I am talking without a loudspeaker, this might be my sound. But if I put a loudspeaker and then talk, then what happens is this. It will be the same quality of sound, but it will be a higher amplitude. It will be a higher amplitude. So more amplitude means louder sound, right? But frequency does not decide that. Okay. So if my friend had more frequency, but I am using a loudspeaker, then I can have a higher amplitude. So amplitude is this. I hope you remember, students. This was amplitude, while this is the time period. So frequency is decided by this, while amplitude is decided by this. So what decides the loudness is the amplitude, and what decides the pitch is the frequency, students. All right. So keep all this in mind, note down the important stuff that you see, and then we move forward. All right, students. Now let's talk about again different comparison that we have to do between solids, liquids and gases, because thankfully sound can travel through all mediums, solids, liquids and gases, all of them, isn't it? So it depends. If the particles are closer together, it seems easier for the vibration to pass on to the next particle, right? But if they are a little far apart, then it looks a little more difficult, and if it is further apart, then it looks even more difficult. So that is how you can relate that why sound should travel faster in solids than in liquids and than in gases. So sound majorly or mostly travel fastest in solids and with least speed in gases. So sound travel faster in solid than in liquids than in gases. Sound speed increases as the temperature increases. Specifically, we are talking about gases here. So what happens is, you should keep it in mind that in summers the sound will travel a little faster as compared to winters. Okay, there is a slight difference. Sound travels more with a more speed if the temperature is more. Just keep that in mind. In the eventual classes in grade 11, 12, you will also discuss why exactly that happens. But right now it is beyond our scope, but we should be at least knowing this as a fact. Okay, last thing, that what do you refer sound as? So sound, so this vibration that we are creating, these are called pressure waves. You can call them as pressure waves, because when I am talking, I am eventually disturbing the pressure in the air of my room. So if this vibration lies between, let's say, 20 hertz to 20,000 hertz, only then our eardrums will be able to sense that. If it is more than 20 hertz, then the vibrations are going to be there, but we will not be able to perceive it. That is not in our, limit. So our eardrums won't be able to reframe that in the form of electrical signals to send it to our brain. So 20 to 20,000 hertz is what we refer as sound. This is sound for us, for humans. Okay, this is our audible range, not our vocal range. Vocal range is what we can produce by the vibration of our vocal cords. That is even a subset of this. So many sounds we can hear, but we cannot produce them. We can almost produce sound between 300 hertz to 3000 hertz, something like that. It might be a little different for different people, but like 300 to 3000. So it is very small range as far as our vocal range is concerned, but our audible range is quite big here, 20 to 20,000. Keep that in mind. So any pressure wave, any sound wave, if you can call it like that, but that's above this 20,000 hertz, then we call it as ultrasonic. We call it as ultrasonic. While if anything is less than 20 hertz, we call it as infrasonic. Many animals can produce these sounds, but that is not in context of human beings, so we won't refer it as sound in general. So infrasonic and ultrasonic, infra means less, ultra means more. That is why ultrasonic means above sound frequency, infrasonic means below sound frequency, right students? There's one more term, I don't know if you have heard of it, supersonic. So students, supersonic has nothing to do with sound. Like supersonic in a way is not about a characteristic of sound or pressure wave. Supersonic is basically any object that can travel even at a greater speed than sound in air, right? So any aeroplane, any fighter jet, any rocket that can even travel at a speed greater than speed of sound, we refer to that object as a supersonic object, right? So keep that in mind as well, just for your general knowledge. Now I have given you some data here just for a quick comparison, just to give you a fair idea that sound travels at a speed of 330 meter per second in air. It looks quite huge, because if you think about it, it is like 3 seconds and it will travel 1 kilometer, right? Because 330 meter in every second will make it 1 kilometer in 3 seconds. That's quite huge. But when you compare it with light, it is way small. That is why any observation, let's say any firecracker, right, you see, you can easily observe it first, but you will hear it sound quite later. Or lightning in the sky, you can observe the lightning very quickly, but its sound reaches you after a delay. Why? Sound travels slower, light travels faster. Okay, but right now we are not discussing light, we are discussing sound. So you can clearly see in water it is 1400 approximately. So it's more than iron, steel. This is even more. So you should be knowing this, that sound travels around 330, until steel it goes up to 6000, right? So I've covered everything, students. I hope you are able to understand whatever I was referring to. So this and this we cannot hear, but this we can hear. Again reminding you, 20 hertz to 20,000 hertz. Right students? So next thing, reflection of sound. There's not much to say, because you have already studied what reflection is. Whenever I am talking, there is a continuous reflection from the walls, right? But it gets reflected in all directions, right? In all directions. So you are not able to realize that reflection easily. You can only realize that reflection easily if there is a huge distance between you and the walls. Then what happens is, there is a delay in the original sound that you hear and the reflected sound. So that is what we refer as echo, right? Listen to this carefully. Imagine you are in a room, but the room size is like moderate, not very huge. Then you will be able to hear your reflected sound and your original sound together. Why? Because there is a limit of perception. So what happens here is the sound signal remains at your ears, and what happens is reflected sound and the original sound merge, and you don't feel the difference. But if the walls are far apart, then the original sound and the reflected sound can be differentiated. It will come with a delay. That is what echo is. So echo is also reflection of sound. Right now also reflection of sound is happening in my room, but I can't listen to that reflected sound in like separately, because the original sound and the reflected sound are almost reaching my ears together. Okay, so sound waves are reflected well from hard flat surfaces such as walls or cliffs. Of course, sound reflection obey the same laws, so you do know that frequency not changes, wavelength does not change, and frequency does not change, wavelength does not change, and speed does not change. All three does not change. Amplitude can change, because then we don't know how much of sound is being reflected. But do understand that, you know, wave speed, frequency or wavelength, these do not get affected. Whenever reflection happens, all these three remains the same, students. Okay, the reflected sound causes echo, right? So it may cause an echo if the obstacle is a little far from you, like approximately 17 to 18 meter apart. That is when you will have a significant delay between the original sound that you are listening to and the reflecting sound. Okay, so keep that in mind. Reflection just affects the direction of sound, right? It does not affect the wavelength, it does not affect the wave speed, it does not affect the frequency, right, students? You do understand that. We will do numericals on this and you will have a better clarity of things, but right now you should understand what reflection of sound is. It is just reflection as we have discussed in the previous class. Alright, students, let's move forward very quickly then. So the captain hears the echo after 11 seconds from original sound of foghorn. What is the distance between the mountain and the ship? You can try it yourself. I can wait. So what is happening here is a foghorn is being sent, and let's say like this, and the sound wave is being reflected like this, right? So it is given that there is an 11-second delay. So if it is 11-second delay, then what are we wanting to find? The distance between the ship and the cliff. So students, 11 seconds it takes for sound to go back and forth, right? So it is like this. So is this distance being covered once by sound or twice? Of course it is twice. So can we say distance is equals to speed into time? Of course we can. Now what is the distance? So distance is going to be 2d, where d refers to the distance between the ship and the cliff. So speed is v and this is the time. So we can write v into t over 2. That is the distance d. Or what you can do is you can also imagine this as let's say if it is symmetrical, then and the ship is not moving right now, then we can call it like 5.5 seconds forward and 5.5 seconds backward, since it is 11 seconds for sound to go back and forth, right? But right now we are doing it by this. Now what is the speed? 330. What is the time? 11 divided by 2. But are you able to understand why are we dividing it by 2? Let's do it very quickly then. 330 multiplied by 11 and then divided by 2. So what I am getting is 1815 meter, and if we round it off to 2 significant digits, then that is like 1800 meter, right? That is the distance between the ship and the cliff, as you may see, or the mountain. Okay, I hope you are able to understand what echo is. It is basically reflection. It is sufficient time. It is more than 11 seconds. If it is less than 0.1 second, then you cannot differentiate between the original sound and the echo. But it is 11 seconds, so it is huge. So easily your echo will be heard quite later after your original sound, right? I hope you are able to understand, and this is something which is very important, this principle of echo or reflection of sound. You know, ships and submarines do use that for navigation, for ranging. That is what we call as sonar. Not exactly we use sound, we use ultrasound for this. We use ultrasound. But imagine when a submarine is traveling through the water, the visibility is almost zero. So when submarine has to travel, it continuously, you know, keeps sending ultrasonic waves and receiving them back just to get an idea that where the obstacles are, right? So I will wait, you copy this down and then we will move forward. I hope you are able to understand this. We will talk about sonar in detail, which is nothing but sound, navigation and ranging. You might be wondering what this is. Sound, navigation and ranging. That is basically sonar. So we are using ultrasonic waves for navigation and ranging. Right, students? So next, very quickly then, diffraction of sound. Audible sounds have wavelength of about 1.5 centimeter and diffracts by small size gap. So you do understand, imagine you are in a soundproof room and you have a soundproof door as well, but the door is slightly opened. Even then, whatever you are talking, the other person on the other side will be able to hear you. Why? Because the sound will go through that opening, right? And it will bend. So even if there is a person here, okay, and even if this is a soundproof wall, but if there is this opening, the sound will be able to reach that person, right? So sound easily gets diffracted. If you remember, we have discussed that in the last class. The condition for diffraction is the gap size should be of the order of wavelength. And since sound has wavelength of the order of centimeters, meters, it is very easy for sound to diffract through normal obstacles that we have around, right? That explains why we hear sound round corners. Low frequency or longer wavelength notes are diffracted more, as we have discussed, because more the wavelength, easy the diffraction. Again, I am repeating, more the wavelength, easy the diffraction, right? So if the wavelength is, let's say 20 centimeter and the other wavelength is, let's say 4 centimeter, then this sound will get diffracted more easily as compared to the second sound, right? You do understand that? So longer wavelength or low frequency gets diffracted more. All these small things you should know to gain that confidence on questions on waves. And don't worry if you are unable to, we will have a series of previous year questions being discussed where we will tackle all such small concepts in the form of questions again. So there you will be able to build up confidence if it is not possible for you to do that right now. Okay, students, copy this down, then we move forward. So you can just write what is diffraction. You already know it is the bending of a wave around the corners, and then you can write this. Right, students, very quickly then let's move forward. So refraction of sound waves, so it is again nothing new for you. It is basically the change in direction of sound whenever it travels from one medium to another. Refraction is caused due to change in speed. So now let's talk about refraction in detail. So whenever any wave is traveling from one medium to another, it changes its path. It changes its path. That is what refraction is. So when refraction happens and you reach from one side to the other, of course the speed also changes, and so does wavelength. Wavelength also changes. But what does not change, students, is the frequency. So we have discussed that in the last video as well, in the last class as well, that frequency does not change. Speed changes, wavelength changes, frequency does not change. But right now it's like solid to gas, for example. So solid will have more speed of sound, means more wavelength, means more wavelength. Can you realize that? Let's say this is a series of compression and these are also compression. So what you can see, the gap is more, the gap becomes less. So when you go from solid to gas, the speed decreases, and so the wavelength also decreases. Why, students? Why? Because you do understand that V is equals to F lambda, and if F is the same, then V is proportional to lambda. So if lambda decreases, the speed decreases, the wavelength also decreases, right? And whenever this happens, students, whenever this happens, keep it in mind. Let's say this is the angle of incidence, then this is the angle of refraction, as we just referred to it in the last video. So what happens is there is a bending towards the normal, though we will discuss this in detail in light, but right now you can just refer to it that when light is going from, sorry, when sound is going from solid to gases, the speed decreases, and that is why sound bends towards the normal, that is refraction. Okay, so solid to gas, of course, what happens is the wavelength decreases, the wave speed decreases, frequency does not change, and it bends towards the normal. And vice versa, of course, when you are talking about sound traveling from gas to solid, then you expect the opposite, right? But what is the important thing to note here? That sound travels faster in solids than in liquids and then in gases, right, students? So refraction is basically the bending of sound when it suddenly changes its medium. Right, students? So I hope you are able to understand everything so far. Then, so I have already talked about it. Let me quickly revise that again. Loudness indicates the sound energy reaching the ear. Louder sound has larger wave amplitude, right? Then pitch indicates the sharpness of sound. So it's like sharpness. Any shrill voice. Someone has a shrill voice. That means what? So that is high frequency, high pitch. Someone has a blunt voice. So they have a lower frequency, lower pitch, like an opera singer, right? Sharp sound has high frequency and consequently high pitch. So pitch is basically a qualitative term in context of the listener. High frequency is high pitch, low frequency is low pitch. Higher amplitude is louder sound, lower amplitude is quieter sound, right? Alright, students, so not much to talk here. Next, application of ultrasound. So sonar, sound navigation and ranging is a method used to measure the depth of water or to locate an underwater object, as I have told you. Right, students? What is the next thing? Figure shows how this works. So you can understand we are relying on reflection of ultrasound now. Ultrasound also travels with the same speed, that is approximately 1500-1600 meter per second in water, and we do know the speed, so we can get an idea of the depth. How? Let's say the depth is d, then again at t is equals to 0 ultrasound is produced, and t is equals to t, it is received again. So again applying distance is equals to speed into time, students. Distance is equals to speed into time, so the distance is going to be 2d, speed is v, and since we know the time, we can calculate the value of d. Right, we can calculate the depth. This can be crucial for some submarines or ships when they are navigating. So this is also used not only for ranging, that is approximating the distance, but also realizing if there is an obstacle and how this ship has to maneuver or to change path. Right, students? So a pulse of ultrasound is sent down from a boat and reflects from the seabed. The time taken for the reflected pulse to be received is measured. This is used with the speed of sound in water to calculate the depth of water, as I have told you. We know the speed, we know the time, we can approximate the distance. Ultrasonic waves are partially reflected from boundaries between different material, such as the chamber of a patient's heart or a fetus. Now this is very crucial. This has brought a revolution. So while the fetus is there, rather than relying on any other form of diagnostic tools like x-rays or something like that, which can be really harmful for the fetus, ultrasound provide you with a way safer alternative. So it is safer to be used, the fetus does not get harmed, and you can in a way image the whole fetus. Why? Because ultrasound gets reflected in different fashions at the boundaries. So you can realize the boundary, and then the computer do the softwares do the rest. They create the whole image just on the basis of the reflection of the ultrasound. So whenever you talk about ultrasound being done for fetus, or maybe in general to examine your stomach, so that is what it is doing. Now you should know it, that ultrasound that gets reflected, and by the reflection we can make an idea of the boundaries and any other obstacle or object that is inside, right? So computer analysis of the reflected waves produces an image, right, students? So it is used for navigation, it is for ranging, it is used for examining body parts like heart, etc., and also for fetus examination, which is a major application of ultrasound. Right, students? Then very quickly, let's do this question. I don't see any problem whatsoever. So t, so distance is equals to speed times time, and the distance is going to be 2d. Why 2d? Because it is sound being reflected and coming back, so it is like back and forth, right? And the speed is like 1500 and the time is 3 seconds. So it is the echo. Echo basically refers to the reflection, and that reflection happens and there is a delay, and we can easily differentiate between the original and the delayed sound. Okay, so d is going to be 1500 into 3 over 2, so that is going to be like 4500 over 2, so that is going to be 2250. I hope I've done it correctly. It was 3 seconds and we have to calculate the depth. So now the ship will have an idea, or the boat will have an idea, whatever it is, that you know the seabed is like this much away. Sometimes it can give you a false reading. Why? Because there might be another obstacle like any aquatic animal or something like that which can reflect a sound or the ultrasound. So what normally people do is they don't rely on one reading, they do multiple readings, and through that they get a better idea. So that if there is any abrupt error that happens because of any other obstacle in the water, that should be known, right? So we don't rely on one reading. It is not easy. You don't rely on one reading. You do multiple experiments. You do it multiple times, and then you take the average, right, students? All right, now let's quickly end today's class. So material testing, ultrasound can be used to detect flaws inside material. Again, in the same fashion, a small crack in a metal girder could cause a building to collapse. This is just to fascinate or elevate the importance of this topic. So any crack, of course, in the walls, in the pillars, in the ceiling can be a big problem later. So if there is an or in railway tracks, for that matter. So what is done is that railway tracks are continuously being scanned, okay, and if there is any abruptness in the reflection of ultrasound, then people would know that there is a crack over there. All right, so figure shows ultrasound being passed through an uncracked and a cracked metal. If it is uncracked, then of course there is a regular pulse that is being received and there is no abruptness. But if there is a crack, then the ultrasound might get reflected earlier and the pulse might abruptly change. The pulse means the recreated image of the reflected ultrasound. So if the reflected sound does not match as per the previous pulses, then obviously there is some abruptness that has happened and there is a crack that has reflected the sound. So reflection happens every time there is a change in the medium. So this crack is like a change in the medium. Suddenly iron changes to let's say an air gap, so that creates an abruptness in the pulse. This is an oscilloscope basically. So this oscilloscope is a mechanism to reconvert that sound into the form of voltage pulse or a display of voltage where you can continuously track. You might have seen such oscilloscopes in hospitals where you can continuously track some variation with the help of digital or analog pulses, which we will study in the coming up classes. But I hope you are able to realize this importance. That is how even X-rays work, even though we will discuss that in the next class. But even X-rays work like that, where we talk about reflection of X-rays. Right now we are talking about reflection of ultrasound. Right, students? We'll do one bonus question before we end today's class. All right, students. Last question before we end today's class. Figure shows two boys A and B standing in front of a tall building. Both boys are facing the building, right? When boy A claps his hand once, all right, boy B hears two claps that are 2 seconds apart. So can you realize why the boy B will hear two sounds? So one sound, because when you clap, you are basically creating sound waves in all directions. So one sound is being received by boy B in, let's say, time t1, and the other will get reflected and then received, let's say, t2. So what is the difference in these two? That is 2 seconds. So what should be t1, students? So it is like traveling 200 meters, right? When straight away the sound is reaching. So t1 is going to be again distance over speed. So distance is like 200 and the time is the speed is like v, which we don't know, that we have to find out. Now what is t2? Again, distance over speed, but obviously the second sound is heard because of the echo. Since clap is only happened once, so the second sound is because of the echo. So what is that going to be? So 350 meter, then again 350 meter, and then again 200 meter, right? So can you realize that the distance that this one is going to travel is going to be 350 plus 350 again plus 200, and that is this. So this t2 minus t1 is like 2 seconds, isn't it? So can we write this as 900 over v minus 200 over v equals to 2. This makes it 750 over v equals to 2. Sorry, 700. Right? I hope you are able to understand. So 700 over 2, this is going to give me 350 meter per second. Now you might wonder, I had written 300 over there, but then with temperature there is a slight variation, so it can also go up to 350. Right, students? So I hope you were able to understand whatever I had conveyed today about sound. You do understand it is a longitudinal wave, it is a mechanical wave, it cannot travel in free space in vacuum, it can only travel through solids, liquids and gases. These are longitudinal, hence compression and rarefactions are formed. Diffraction of sound, refraction of sound, reflection of sound. I hope you are able to understand all of it. Right, students? Thank you so much for your time. I hope these videos are helping you achieve your desired result. And if not, then do let us know what else should we do or how we should change things for you, which can be more helpful and more relevant for you guys. Right, students? Thank you for your time. I will see you very soon. Bye-bye. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.